gas will be constantly, continuously flowing over the stationary phase. Now, depending upon the type of stationary phase and mobile phase, we can classify chromatography in different types. So few important types are shown. There are many more also, but I am showing only few important types. If you are using a mobile, if you are using an inert gas at the mobile phase, and if I am using a solid material as a stationary phase, the principle of separation is based on adsorption, and the technique is known as GSC, gas solid chromatography. And as I told you, this is a technique that we are mostly using for gas analysis. Again, we are using a gas as the mobile phase, and then we are going to use a liquid, an organic liquid as the stationary phase. The principle is different. It is based on partition. And the technique is known as GLC, gas liquid chromatography, which is more widely used. Gas liquid chromatography, or today people simply call it as GC, but actually gas liquid chromatography. Coming to liquid phase, we are using a liquid as the mobile phase. Most of the time we are using a combination of liquids. And then we can use a solid material as the stationary phase, and the separation is based on adsorption. And again, the technique is known as LSC, liquid solid chromatography. Okay, the students who are using HPLC, and if anytime you used a silica column, is an example of LSC, liquid solid chromatography. We can use a liquid as the mobile phase. We can use a liquid as the stationary phase, and the principle is partition. And it is like GLC, it is LLC, liquid chromatography. We can use a liquid mobile phase. We can use a porous polymer having very precise pore size in terms of angstrom unit. And the principle of separation is based on size exclusion, separating on the basis of size difference of the molecules. And the technique is known as SEC or GPC, gel permeation chromatography or size exclusion chromatography. A wonderful technique, especially in the field of polymer analysis, polymer chemistry. You can get different lot of information about different types of polymers, like average molecular weights, polydispersity, molecular weight distribution. Lot of valuable information regarding a polymeric molecule can be available from a GPC or SEC analysis. Then we can use a liquid as the mobile phase. We can use an ion exchange resin. And the principle of separation is based on ion exchange. It can be cation exchange or anion exchange. And the technique is known as ion exchange chromatography. And then last one is a very simple technique. We are using a liquid, and the stationary phase is nothing but a thin layer of silica, uniform thin layer of silica coated on a glass plate or an aluminum plate. And the principle is adsorption, because silica is a wonderful adsorbent. And the principle is based on adsorption, and technique is known as TLC, thin layer chromatography. It's a very good technique for the initial screening of the sample. You will immediately come to know how many compounds are present in your given sample. It's a very, very easy screening technique. TLC has become automated HPTLC. Tomorrow, I think you are going to have a wonderful session on HPTLC. So it's a wonderful technique. So these are some of the important different types of chromatography techniques classified on the basis of mobile phase and stationary phase. And there are others also, like supercritical chromatography. I think day after tomorrow you'll be having a talk on SFC also. Why we use specifically our discussion will be based on GC. So why we are going for GC has got shorter analysis time compared to LC. Analysis time in GC is basically shorter. And we have got plenty of stationary phases. Different types of stationary phases are available for different types of applications and different types of compounds. And wide choice of detectors and comparatively an easy operation. Sir, my voice is audible to everyone? Hello?
Yes, it's audible.
Yes, sir.
Sir, I'm audible to everyone?
Yes, sir.
Audible.
So what are the goals of carrying out GC? To separate mixtures of organic compounds. Especially this can be a slightly misleading statement. So people may feel like only organic compounds can be separated by GC. Even before I go to this slide, I just want to tell them the students should understand. Yesterday I told every analytical technique has got advantages and limitations. So from that point of view, GC has got two limitations. One is it is a technique that is applicable only for volatile samples. That means your sample has to be volatile. You should be able to convert the sample into gaseous form, volatility. You have to heat the sample, convert the sample into vapor form. So sample has to be volatile. Then only GC can be applied. If the sample is totally non-volatile, GC cannot be applied. Number one. Number two is the sample also has to be thermally stable. That means, unlike in HPLC, in the case of GC, more than 95% of the operations are going to be at elevated temperature. We are going to heat the sample because we need to convert the sample into vapor form. And there are certain samples which will undergo decomposition or disintegration when it is heated or when it comes in contact with the heated metallic surface. And these compounds are called unstable, thermally unstable compounds or thermolabile compounds. Again, we have a problem with GC. So these are the two limitations. First of all, the sample has to be non-volatile. And second thing, the sample has to be thermally stable. Unless these two conditions are fulfilled, we cannot use GC for the analysis of that compound. So most of the inorganic compounds are non-volatile because they are highly non-volatile compounds. It can be salts, it can be chelates or metal compound, metal complexes. I mean, so inorganic compounds are most of the time they are non-volatile samples. That's the reason why we cannot use GC for most of the inorganic compounds. But there are few inorganic compounds where we can use GC, but these compounds are already in the gaseous form. For example, atmospheric air. We know the composition of atmospheric air is approximately 79% nitrogen and 21% oxygen. And we can separate this at room temperature using a molecular C5A column and a TCD detector. And we can get two beautiful peaks for nitrogen and oxygen. It is an inorganic separation, but the sample is already in the gaseous form. We can separate carbon monoxide and carbon dioxide. It's a very, very important application in fertilizer industry and petrochemical industry. But the sample is already in the gaseous form. We can use GC for that. So there are very few samples GC, but these samples are already in the gaseous form. Otherwise, barring these few samples, most of the inorganic samples are out of bound of GC analysis. And then we can identify and quantify using reference standard. This is equally applicable for LC also. So you can use the right type of stationary phase. You can get a total separation of different compounds present in the sample. But what are those compounds? GC will not tell you. For that, we require reference standard. The same case in HPLC also. Unless and until we have reference standards with us, we cannot identify the separated compounds, and then we also cannot quantify them. Okay, that's a limitation for GC as well as LC. The reference standards are, but sometimes when we talk about very complex samples like oils or perfumery compounds, where so many compounds are going to come from a single sample, getting standards for all those separated compounds is going to be a very, very difficult task. So that means we can use GC only for getting a proper separation, but identification becomes difficult. And that's a place where MS is going to help us. We are coming to that. Okay. A typical GC system will have a flow controller. We have an injection port. We have a column and column oven. We have a detector and a data processor. Why we require a flow controller? Because our mobile phase is a gas. It's an inert gas like nitrogen, hydrogen, or helium. And we are having a cylinder, a high pressurized cylinder. That's a source of gas. And cylinder is at a high pressure. And we need to control the pressure that is coming to the instrument. We normally adjust a pressure of around 6 kilograms to 7 kilograms per square centimeter on the equipment. So we need a flow controller to control the flow of gas. Then we have an injection port where we are going to introduce the sample into the system. In the case of HPLC, in the case of GC, we are always injecting the sample with a microliter. Either we can go for a manual injection or we can go for an auto injection. Nowadays, we prefer auto injection. But there are people who do manual injection also. Then there is a column. When I say column, I am always referring to stationary phase. Because stationary phase is always present inside the column. And the column is always put inside an oven. Then we have a detector. Whatever the separation is actually taking place inside the column, compounds will get separate. Compounds in the given sample will get separated inside the column. They will come out at different times from the column. And when they come out, they will enter the detector. And the detector is going to give an electrical signal, which is proportional to the concentration of the compound. And that is processed by your data processor. So in the case of a GC, we have three different heating zones. Injector port is heated because the user has to optimize the temperature of the injection port. Different samples will have different injection port temperatures. You have to optimize it. So it has got its heater. Column is also to be heated. That's the reason why we are putting the column inside an oven. So oven has got its own heater. And the detector is also to be heated. And so we have three different heating zones, one for injection port, one for the column, that's the oven, and one for the detector. Then what is the mechanism of zone migration? This is the essence of separation by chromatography in general. Whether you are going to separate it by GC, whether you are going to separate it by LC or any other chromatography technique, basically, why do you get a separation when you are introducing the sample into a chromatography system? It is because of mechanism of zone migration. What does it mean? I'll just read the sentence and tell you. Chromatography separation is due to the differential migration rate of components in the mixture. That means for the students to understand in a very, very simple manner, suppose I got a binary sample which contains A and B. Two different chemical compounds are present in my sample. I'm going to introduce the sample into my chromatography system. It can be GC, it can be LC. So when it goes inside the system, it goes to the column, and the column contains a stationary phase, which is also nothing but a chemical compound. So there will be, so when the sample gets into the column, the compounds present in the sample will have a physical interaction with the stationary phase inside the column. And different compounds will interact in a different way with the stationary phase. So now assuming that your sample has got two compounds A and B, two different compounds, when it goes inside, you imagine compound A has got a larger affinity, a greater degree of affinity toward the stationary phase. That means it likes the stationary phase. That means it will try to remain in the stationary phase for a longer time because they like each other. On the contrary, the second compound, compound B, does not like the stationary phase. That means there is no proper affinity, there is no proper liking, there is no proper bonding. So it doesn't like the stationary phase, so it will not like to remain inside the column for a longer time. It would like to come out faster. So that means depending upon the difference in the degree of affinity, these two compounds, compound A and compound B, will be moving at two different rates. Because B has least affinity, it is moving faster because it wants to come out faster, whereas compound A will move very slowly because it has got a larger affinity toward the stationary phase. It wants to spend more amount of time with inside the column. It will be moving slowly. So that means two different compounds having two migration rate inside the column because of the difference in the degree of affinity toward the stationary phase. And this is a very basic mechanism by which the separation is happening, whether it is a GC column or LC column. Okay, now when I'm talking about a binary compound, it is very, very simple. There are only two compounds to be separated. I can optimize it without much problem. But when I talk about a very complex sample as a naturally occurring compound, you talk about an essential oil, a perfumery oil, or a medicinal oil, and where different compounds, I mean, sometimes a perfumery oil can give you more than 100 compounds in the sample. So if I need to separate 100 different compounds using a stationary phase, all these 100 compounds should move at 100 different speeds. Otherwise, I will not get a proper separation. Many compounds will move together. That is what is known as overlapping in the case of chromatography. So column selection becomes very critical. That is, whether it is a GC analysis or a LC analysis, column selection is very, very critical. You should know what is the column chemistry and what is the sample chemistry, and there should be a proper match between these two. Okay. Now, general chromatography question. When you are introducing a sample into the chromatography system, it undergoes a distribution between the stationary phase and the mobile phase. So there is a general chromatography equation like Xm is in dynamic equilibrium with X. What is XS? It is the, so X is the molecule. X is our sample molecule or the compound molecule. So XS is nothing but the molar fraction of the sample in the stationary phase, and XM is nothing but the molar fraction of the sample in the mobile phase. So there is a equilibrium between these two molar fractions. Now, by optimizing the conditions, which is the job of the chromatographer, the analytical chemist, when he is actually optimizing the conditions, what we are trying to do, we are trying to take out the sample from the stationary phase into the mobile phase, so that it can flow out of the column, go to the detector, and gets detected. And that's a whole optimization process. See, when you please understand, students, I mean, in the case of spectroscopy like UV or IR, there is not much of optimization. In the yesterday, we also saw the UV. You should know what is the lambda max. You prepare the solution, keep it inside the sample compartment, and read the absorbance value at the given lambda max value. That's all. There's nothing like optimization of the method. But when it comes to LC and when it comes to GC, there are a lot of optimization process involved. Lot many parameters are to be optimized. So it is going to be a time-consuming work. It's going to be a time-consuming job. So sometimes we may take a longer period of time to optimize a sample and get a meaningful separation of the compounds in the given sample. Just 1 minute on a column, because a column is the most important part of the system. When you talk about a chromatography system, column is the heart of the system, because it is the column that is going to give you separation, not the injection port, not the detector. You must be having a very powerful software, but unless and until you select the right type of column, you will not get the right type of separation. From that point of view, column is considered as the heart of the system. And please understand, column is a consumable item. It is not a permanent thing. It's a consumable item. Over a period of time, you need to replace the column. You have to throw it out and buy a new one. When it is, it depends on so many factors. We can maybe, it depends on so many factors. Okay. So there is something called column efficiency. People say my column is very efficient. What does it mean? Column efficiency is nothing but it is related to the sharpness of the peak. Every chromatographer wants the peaks to be very, very sharp and narrow. And if your column is giving very sharp peaks, that means your column is very, very efficient. And column, as I told you, it's a consumable item. You're going to use the column day in and day out for different types of samples over a period of time. Slowly over the usage, the column efficiency is going to decrease. And one point of time, you may have to replace the column, because after some time, after usage, the sharpness of the peak will be lost, and the peaks will start becoming broader and broader and broader. And that means the column is losing the efficiency. And if the peaks become broader, resolution will be lost. That's a major concern. Resolution will be lost. Your reproducibility can be a problem. And that's the time when you have to think of replacing the column. So column evaluate, because we can talk on this topic for the whole day. So I am not going to spend too much of time because of the limitation of time. So column efficiency, there is a variable called N value, number of theoretical plates, based on which we can actually quantify the column efficiency. So N value, N is the number of theoretical plates, and that is that gives an idea as to what is the efficiency of the column. Higher the value for N, better will be the efficiency of the column. And there is one more variable we can use, which is known as HETP, height equivalent to one theoretical plate. That also is another variable we can use to define the efficiency of the column. Either the N value has to be very high, or HETP value has to be very low. So these two terms we can use to define the efficiency of the column, and the column efficiency is related to the sharpness of it. Sharper the peaks, better will be the resolution. And your sensitivity also can be very, very high. You can actually, the peak height will be increased. Then there is another factor known as stationary phase efficiency, solvent efficiency, or it is also called selectivity. Because if I am getting a stationary phase, that means a column, and if I am having two different compounds having, say, very close boiling points or close polarity, whether the stationary phase is able to separate these two compounds satisfactorily or not. And that is what is given by the selectivity of the stationary phase. And the third parameter, which probably is very common in chromatography terms, peak symmetry. Tailing factor, I think many of the students are using HPLC, that's what I understand. So they will know what is by peak tailing. Tailing is an accepted phenomenon in chromatography. See, tailing, basically, any chromatographer would like to have a Gaussian peak, a symmetrical peak. A symmetrical peak means when I'm getting a peak, it should be like an isosceles triangle. If I'm dividing the peak by dropping the perpendicular of the peak maximum, the triangle, the perpendicular should divide the peak into two equal halves. Equal halves. That means it is called it is a symmetrical peak or a Gaussian peak, and that's what we want. And many times we don't get it. The most of the time, what is our observation is when we are dividing the peak by dropping a perpendicular from the maximum point, the second half of the peak is slightly wider as compared to the first half, and then we say peak is tailing. Tailing is accepted. Even USP has also got certain limit for tailing, and beyond which it is not accepted. If too much of tailing comes, again, our reproducibility of results will be a problem. So too much of tailing comes, there are some ways and means by which we can try to reduce the tailing. So those are a lot of things we have to discuss about that. So there is something called tailing factor also. Okay, these are pertaining to the column. Finally, we are coming to resolution. Resolution is the most important requirement. We want a complete resolution because resolution gives information. Yesterday also we speak about we talk about resolution in spectroscopy also. Okay, we talk about resolution in chromatography also. So resolution gives information, and resolution R, there is an equation shown there. That's a universal resolution equation. And this resolution is influenced by three different parameters. One is the efficiency, that is n value. I already told you that is related to the efficiency. Then selectivity, that is alpha factor, and that also I covered. And capacity factor, small k. What is meant by capacity factor? Capacity factor will give you an information as to how much time the compound will be retained by the stationary phase. That means when the compound goes inside, how long that compound will be retained by the column. This information will be given by capacity factor. And all these factors, n value, k value, and alpha value are appearing in the equation. So ultimate resolution is governed by, is influenced by three different factors. So by optimizing these three factors, we can actually maximize the resolution also. So ultimately, when we talk about resolution, it's always between a pair of peaks. Resolution is always, we are looking at resolution between two different peaks, two peaks, a pair of peaks. So when the resolution, I have shown different on the screen, you can see resolution is equal to 0. That means practically no resolution between these two compounds. They are coming very close to each other. We are improving, you are optimizing the condition further. We are getting a resolution is equal to 0.5, not acceptable. Further improvement, modification of the method, you are getting R is equal to 1, resolution is 1. Again, not acceptable because it is only 90% resolution. And if you are able to get a resolution value 1.5 or more than 1.5, you are getting a complete baseline separation, and that is what we want. So we always recommend, we always tell our people, customers, users to optimize the conditions in such a way that you get a resolution value of 1.5, and that's a 100% baseline separation. And there are different ways also by which we can improve the resolution. We are not going into those details. Coming specifically to GC, we are using a mobile, we are going to use a inert gas as the mobile phase. The mobile phase is also called as the carrier gas in the case of GC. And the gas has to be inert, and it has to be very, very pure. And we don't have much choice. We have only maximum 3 different types of gases that can be used: ultra pure nitrogen, helium, and hydrogen. Actually speaking, hydrogen is supposed to be the best carrier gas in the case of GC. But probably people are not preferring to use hydrogen because hydrogen is also an explosive gas. Because GC involves temperature. You are going to heat the column, you are going to raise the temperature. And if there is unfortunately, there is a minute leakage of the gas, carrier gas, that is hydrogen inside the oven, I mean, it's going to be a very unpleasant situation. So people are a little scared about using hydrogen, even though that is the best carrier gas in case of GC. And next to hydrogen, the best one is helium. Helium is also not normally used in the case of GC because of the cost. Helium is extremely costly, and that's the gas we are going to use in GCMS. Okay, but in the case of GC, an option, most of the people in industry also, they use ultra pure nitrogen as the carrier gas. But all these gases should be very, very pure. I mean, it should be 99.99% pure because high purity gases are required in the case of chromatography. And column is made of different types of materials. You can use stainless steel. Stainless steel columns are available. Local columns are available. These are known as pack columns. Local columns are available. It will be available in Bhopal also. They are available in Mumbai. Everywhere it is available. The local manufacturers are there. But they will, you tell them what is the type of column you want, they will pack it and give you. It's very much economical. They are called pack columns, but they are not very efficient also. They cannot be used for very, very complex samples. Okay, so, but at the same time, they're very, very cheap. Then columns can be made of glass. Glass is supposed to be a wonderful material. It is a totally inert material, but the problem is a fragility. Fragility means it can easily break. So handling is a problem. Then we have got capillary columns made of fused silica, and fused silica columns are today's most of the columns available in the market. Capillary columns are all imported columns. There is no local manufacturer. Most of the capillary columns are imported, and these are all mainly made of fused silica. It is more flexible than glass. At the same time, it is as inert as glass also. So today's scenario in industrial usage or academics also, when we are talking about very, very complex sample analysis, people prefer a capillary column because it got a lot of advantages over a pack column, locally available pack column. Okay. So types of pack columns can be maximum 5 meter long, by 5 meter long columns are also very rare. Normal pack columns, people what they use is 1 meter or 2 meter. That's the normal practice. And the diameter of the tubing can vary from 2 millimeter to 4 millimeter. Imported capillary columns, the length is starting from 10 meter, and today we have columns which are more than 100 meters. Okay, very, very long columns are available. And the ID also, you can see it is just 0.1 millimeter and it can go to 0.53 millimeters. So different ID columns are also available. And depending upon the internal diameter of the tubing, capillary columns are also divided into micro bore capillary column, narrow bore capillary column, wide bore capillary column. So therefore, different types of capillary columns are available for different types of applications. So I'm just spending 2 minutes on this column because it is a very important part. Main types of capillary column, there are two types. One is called a PLOT column, porous layer open tubular column. All capillary columns are called open tubular column because it is an open tube. Then students may wonder, where is the stationary phase? If it's an open tube, where is the stationary phase? The stationary phase is coated as a very, very thin layer on the inside surface of the tubing. The tube is like a cylinder. It's a cylinder. It's a tube. So inside surface of the tubing is coated with a very, very thin layer of the stationary phase, and the thin layer coating thickness can go into only micrometer. Micron thickness coating is given internally, the coating of a stationary phase. Otherwise, the tube is open. That's why it is known as open tubular column. You can see that here. So porous layer open tubular column and wall coated open tubular column, PLOT column and WCOT column. PLOT column, you can see the red color, that the red ring is the fused silica tubing. And inside you can see small particles. It's a circular way, it is coated on the inside surface of the tubing. These are all very small particles of adsorbent material. Solid particles are coated as a thin layer inside. And this is an example of the GSE column. I remember gas solid chromatography column. And these columns are normally used for gas analysis. I told you GSE technique, solid stationary phase is mainly used for gas analysis. So this type of capillary columns, PLOT columns, porous layer open tubular columns, they are basically used for gas analysis. You can see the coating inside of very fine particles of a adsorbent material. But whereas the second one, wall coated open tubular column, the blue line I am showing it as the silica tube, and you can see a internally there is a small yellow coating inside. That is the stationary phase coating. And that coating can vary from say 0.1 micron to even 5 micron. But it is in micron thickness, that's all. The stationary phase is coated as a very, very thin film internally. And that coating is shown as that yellow patch inside. And wall coated open tubular column is the one which we are using for most of the analysis. You talk about a pharmaceutical analysis, you talk about a perfumery sample analysis, you talk about food chemistry sample analysis, most of the time you're using a wall-coated open tubular columns. And what are the stationary phases for you're seeing? Most of the stationary phases are polymeric in nature. And most common for WCOT columns, there are two different types of polymeric materials we can think of. One is a polysiloxane, that is silicon polymer, polysiloxanes. And the second one is polyethylene glycols, PG columns. And they are also known as wax columns, polyethylene glycol columns. Polyethylene glycol columns are highly polar columns. You have to very judiciously use it. Okay, whereas polysiloxane columns have got a much higher temperature stability. So these two types of, for example, polysiloxanes, any polysiloxane column, if you take the backbone is an oxygen, silicon, oxygen bonding. You can see that oxygen, silicon, oxygen, silicon, oxygen. It's a polymeric chain. It's a backbone. That's the backbone of the column. And on this backbone, we can attach different groups. R is a group. If R is all R's, the group is methyl group, CH3 group. And if all the attachments are all methyl group, it is a 100% methyl silicon column. And R can be a cyanopropyl column, cyanopropyl group, CH2, 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 CN. It becomes polar also, cyanopropyl group. R can be CH2, CH2, CF3, trifluoropropyl. It can be a phenyl ring. So depending upon the type of the attachment on the backbone, silica backbone of the column, we can create the columns having different polarity also. And some of the columns are 100% non-polar. For example, 100% methyl polysiloxane column is a non-polar column. But when you talk about trifluoropropyl and those type of columns, there is a polarity involved. So for different types of samples, we require different types of columns. So that is why you should know what is the column chemistry and what is the sample type. There should be a proper match. Otherwise, the separation will not come. A very common column is an example of a very popularly used column is 5% diphenyl modified, 95% dimethyl polysiloxane. Okay, you can see the structure also here. And different trade names are available, RTX5, HP5, SPB5, different columns are available from different manufacturers. But that 5 stands for 5% diphenyl modification. Similarly, there we have got 50% diphenyl modified, 50% dimethyl polysiloxane column. Different columns are available for different types. So you should know what is the column to be selected for your sample. And there are columns specifically designed for mass spectrometer use also. And those columns are known as MS columns, DB5MS, RTX5MS. Why that MS attachment is given? We are incorporating a phenyl group inside the silicon, oxygen silicon backbone. By incorporating a phenyl group in the backbone itself, we are getting better temperature stability. And that is supposed to give very low bleeding. They are called very low bleeding columns, and they are normally used in the MS, GCMS. So that is the reason why they are called DB5MS column, RTS5MS column like that. And then we are coming to polyethylene glycols, very, very highly polar columns. Wax columns are there, FFP type columns are there. FFP is nothing but free fatty acid phase. They're also highly polar columns. And all these polar columns you have to be very, very careful because their temperature, they are very, very less temperature stable thermally. Compared to polysiloxane columns, silicon polymer columns, they can go to very high temperature like 350 degrees and all, and they're quite stable also. Whereas a polyethylene glycol columns cannot cross, say, maybe around 275 or 260 degrees. More than that, it cannot go. So you have to be very, very careful but these are wonderful columns for separating separating polar compounds. See, in chromatography, the separation takes place on the base of like dissolves like. In homeopathy treatment, we say like cures like, because if an arsenic poisoning, their antidote is also arsenic. They say the like cures like, and whereas the case of chromatography, we say like dissolves like. So if the polarities are matching, and there will be better separation. So polar columns are preferably used for polar compounds, and monopolar columns are used for non-polar compounds. But there is no hard and rigid bifurcation. I mean, there is no segregation. I mean, but one has to use their own judgment for the right type of selection of column. This is a comparison segment for different manufacturers. I'm just skipping it. And sample introduction, GC can be used for gas analysis. It can be used for liquids as well as solids. Gas can be introduced with the help of a gas stage syringe. Liquid can be introduced with the help of a microliter syringe. And the solid is to be dissolved in a suitable solvent. You have to make a solution, and the solution can be injected with the help of a microliter syringe. Injection ports are also different. When it comes to injection port, the injection ports are different for the local columns and the capillary columns. If you are using a pack column, that's a local column, your injector is different. And if you're using a capillary column, your injector is different. And the capillary column injector also, there are different ways of sample introduction. Split injection mechanism, splitless injection mechanism, programming temperature vaporizer, PTV mechanism, cool on column injection mechanism. There are different ways by which we can introduce the sample into the column. As all, it depends upon what is the type of application, what is the analysis you are looking at. Finally, coming to column oven. Column is always inside the oven. And the case of GC, there are two types of operations. One is isothermal analysis, one is temperature programming analysis. Isothermal means we keeping the column temperature constant throughout the analysis. Like in the case of HPLCs, there is something called isocratic run, where you are keeping the polarity constant, isocratic. Similarly, in the case of GC, is isothermal. And the second one is temperature programming. You are actually starting from a low temperature and then changing the temperature, going at a certain rate of heating to a high temperature, and that's called a temperature programming method. In LC also, you have a equivalent operation. You talk about gradient. You change the polarity gradually. Here we are changing the temperature gradually. There are equivalent operations. Okay. Now, detector, we have got different detectors available in the case of GC. And one point you have to keep in mind is the detector temperature in GC should be at least 15 to 20 degrees more than the final column temperature. Otherwise, sample condensation can happen inside the detector. It will produce a lot of background noise. The sensitivity will reduce. You have to depend upon the service engineer to come and clean it. So detector temperature should be always more than the final column temperature by 15 to 20 degrees. And there are different detectors. Flame ionomer detector is a very, very common detector which have got a fairly good sensitivity for many of the organic compounds. Thermal conductivity detector is there, which is today it is mostly used in gas analysis segment. Flame thermionic detector is there. It is also called FTD. It is also known as NPD, nitrogen phosphorus detector. Then we have flame photometry detector, FPD, electron capture detector, ECD, and finally mass spectrometer detector, MSD. We are coming to that. Okay. And we can use FID for any compound that can be oxidized in hydrogen and air. Or you can say any sample containing carbon and hydrogen can be analyzed by FID. Electron capture detector is a wonder detector in the case of GC. It can go to extremely low levels of detection for electrophilic compounds, electronegative compounds, compounds which have got affinity samples. Any halogenated sample is an electrophilic compound, but they should be in extremely low concentration. Then only we will use ECD. ECD contains a radioactive isotope nickel 63, so to be very careful. Contamination should not take place, and even for so you have to take extra precautions while using ECD. Otherwise, it is a wonderful detector for GC. Can go to very, very low levels of detection. FTD, that is flame thermionic detector, is also known as nitrogen phosphorus detector, selective to compounds containing organic nitrogen or phosphorus. Then FPD is the flame photometric detector selected to phosphorus, sulfur, or tin containing compounds. And all the three, ECD, FTD, and FPD, find lot of applications in food science, in food chemistry. Because today we talk about residual pesticide analysis, a global problem we are debating. Residual pesticides in food products, what all we drink and eat, they all contain pesticide residues. And many of the pesticide residues are chlorinated compounds, are there compounds containing phosphorus, compounds containing nitrogen. I mean, all these different types of pesticide compounds are there. And for those, and these the pesticides are present in very trace quantities. That is why it is called a residue analysis. And these detectors are very, very useful in those analyses, ECD, FTD, and FPD. And finally, TCD, I told you, was a universal detector, but it has got a lower sensitivity, but it is still used as a preferred detector in the case of gas analysis. And the qualitative analysis, you can compare the retention time. Normally, what we do in the case of GC, inject a sample, then we inject a standard under the same condition, compare the retention times, and the retention times are matching, then we say the sample is identified. Even though it is not a very foolproof method, then there is something called retention index also for the qualitative identification. Similarly, we can do quantification by GC and LC, and different methods of quantifications are available. Normalization method, corrected area normalization method, absolute calibration curve method, where we talk about internal standard method and external standard method. So these are different quantification methods available for GC as well as LC. Now let us come to our topic of discussion, major topic of discussion, advantage of mass detector. So please understand, we talk about the GCMS system. MS is acting as a detector for the GC. GC has got a main responsibility of separation, and whatever separated compounds are coming to a mass spectrometer will give an identity. It's an identification technique. Okay. So when you talk about, we have seen the different conventional detectors like FID, ECD, FTD, and all. They are all conventional detectors. They are all very, very, very sensitive detector. But when it comes to identification, these detectors will not help you. They cannot tell you what the compound. They can give you sensitivity. Then it is your responsibility to identify the compound using standards and comparing retention times. And sometimes it is going to be a Herculean job. Many times it may be difficult for you to get standards. So that's a limitation of normal GC. When it comes to extremely complex samples, it's a major limitation of GC because you cannot identify the compounds. Okay, because the non-availability of standards. And even if the standards are available, it's a very, very Himalayan job because you have to sit and inject standard and compare the retention time for each and every pick. It's going to take such a lot of time. So it's a difficult process. And that's the place where mass spectrometer is going to score over a normal conventional detector. Mass spectrometer is also going to give the same degree of sensitivity. We are not compromising sensitivity. At the same time, mass spectrometer also can give you an identification of the compound without the requirement of a reference standard. That's the most important part to be underlined, without the requirement of a reference standard. But then you have to be very cautious, you have to be very careful in this statement should not be misinterpreted as once you purchase an MS, you don't require standards at all. That's a wrong statement. Because when I say standards are not required, I say that is, they are not required only for qualitative analysis or qualitative identification. The moment you say quantification, you want to quantify something, you want to quantify target compound, you require standard. In any analytical chemistry technique, the moment you say quantification, you have to prepare a calibration curve. A linearity curve you have to plot. And for plotting this, you require standards. You have to prepare standard solutions having different concentrations. You have to create a calibration curve, and then only you can actually quantify an unknown compound. So for quantification, standards are required, but for qualitative identification, standards are not required. So this should be very, very clear in your mind. Otherwise, there should not be any problem. Okay. Now, what is a simple definition of mass spectrometry? The basis of mass spectrometry, in short, we can call it as MS, is the production of ions that are subsequently separated or filtered according to their mass to charge ratio and detected. And the resulting mass spectrum is a plot of the abundance of the produced ions as a function of the M/Z ratio. So this definition clearly states that the sample has to undergo ionization. That's why it is stated the basis of mass spectrometry is the production of ions. That means the sample has to undergo ionization. It has to produce ions, or what we normally call as fragments. And these fragments will be having different mass numbers. So when the sample molecule undergoes fragmentation process or ionization process inside the mass spectrometer, it is going to give you different fragments having different mass numbers. So you get a mixture. And all these fragments are to be separated on the basis of their M/Z ratio. And they are all sent to the detector, and the detector is going to give an output, and this output is called a mass spectrum. And the advantage is this mass spectrum is going to be the basis for the identification of the compound. When we talk about a normal GC, retention time is the basis for identification, whereas when we talk about a GCMS, mass spectrum is going to be the basis for identification, because otherwise we don't use retention time for identification. We use a mass spectrum for identification. Once we get a mass spectrum, there are mass spectral libraries available. We have the freedom to go for a search, and then we can automatically identify the compound. And there we are not using a standard. So that's a major advantage of using a GCMS over a conventional GC. Now, what is the basic requirement? The MS detection, the compound has to undergo ionization, and there are different techniques of ionization. We are going to see that. Now, what is the objective of GCMS analysis? Separation and identification of compounds present in the sample. That's a qualitative analysis. So first and foremost, priority, objective is to do a qualitative analysis. You have to get a clean separation. So there the importance of column selection will come. You have to choose the right type of column. The sample has to go into the column. Column has to separate it well. And then all these separated compounds are to be identified. That's a qualitative analysis. Second objective, having received a wonderful separation and having identified all these compounds, the second objective is to find out what is the concentration of each compound. That becomes a quantitative analysis where you require standards. And the third objective is high residue sensitive residue analysis. You talk about, as I told you, an example like pesticide residues in food products, maybe a forensic sample by a bioanalytical application. I mean, basically we are looking at targets which are present in extremely small concentration. Very, very small concentration. Your system should be sensitive enough to identify these compounds and quantify these compounds. They are all basically high residue, sensitive residue analysis. The system should be capable enough to do this. And the 4 S values, one is called sensitivity, one is called selectivity, one is called speed of analysis, and the last one is called solution or total solution. What is sensitive? People all talk about sensitive. My detector is very sensitive, or my instrument is very sensitive. What does it mean? Sensitivity means the change in the detector response whenever there is a change in the concentration of the target. That's your analyte. That's all. What is the simple definition of sensitivity? Change in detector response with change in the analyte concentration. Okay, that means your concentration is more, the detector response is going to be more, and vice versa. And we talk about selectivity, and here also you come across statements like the method is very selective. What is meant by selectivity? Simple definition, relative freedom from interference. That means if a sample contains some compounds which are going to interfere in the determination of your targets, you have a major problem. You talk about food analysis, food chemistry. Most of the food samples, there are a lot of matrix. Matrix means any unwanted compounds. And these unwanted compounds can interfere in the determination of your target compounds. So that means you'll be getting a wrong analysis. Your analysis will not be a proper. It will not be a proper result. So that means your analysis should not be affected by the presence of those unwanted compounds. There will be total freedom from interference. Nothing should interfere in analysis. That is called selectivity. So when I say my method is very selective, I can authentically say that when I'm using this method, for the determination of such and such a target compound, nothing is going to interfere in the determination, and whatever result I am getting is 100% authentic. My method becomes a selective method. Speed of analysis, that is the requirement of today's corporate world requirement. Analysis time is to be reduced, because today when you go to industry, you'll find lot of workload is coming in the it can be a pharmaceutical company, it can be a chemical company. Especially when you go to a busy quality control lab, so many samples are coming, sample load is too much. Suppose imagine one sample is taking in a GC analysis, suppose one sample is taking exactly 1 hour or roughly 1 hour. So how many samples you can analyze in a day? If you are starting from 9 o'clock in the morning and say closing at 5 o'clock or 6 o'clock in the evening, how many samples you can analyze? Because each sample is going to 1 hour. So that means we can analyze maximum 6 samples, or at the most stretching maximum 7 samples. Because there's a heating and cooling time and all involved that is to be taken into consideration. So maximum 6 or 7 samples only can be analyzed during the day. But now, by any chance, if you are able to reduce this analysis time from 60 minutes to 20 minutes, that means in 1 hour time, I can analyze 4 samples. That means end of the day, instead of analyzing 7 samples, I may be able to analyze 25 samples or 30 samples. That means my productivity is going to increase 4-fold or 5-fold. And that is what is today's corporate requirement. Increase your productivity. And we manufacturers are all of this requirement. So we have certain methods by which we can reduce the analysis time without compromising the resolution. So that is what is known as speed of analysis. So we can actually, the speed of the analysis can be increased, so that ultimately you can increase the output. Total solution, when you are buying an equipment like a GCMS or LCMS or whatever it is, and that instrument should give you a total solution for your analytical problem. It should not be a white elephant. It should give a total solution for the problem. It's not just an instrument. It is a total solution provider. Now, when we talk about normal GC, when we talk about normal GC, we are getting only 2 different parameters. We are getting the retention time and we are getting the detector signal intensity. We talk about MS, GC-MS, we are getting one more parameter. We are also getting a mass spectrum. So we are getting retention time, we are getting intensity, and we are also getting mass spectrum. So 3 different, so three-dimensional information we are getting. Flow chart of a GC-MS system SQ. I mean, students may wonder what is meant by SQ, because SQ means a single quadruple system. In GC-MS, we can have single quadruple MS or triple quadruple MS. And what is a quadruple? You will come to know. What is going forward is what is a quadruple. So if a system contains a single quadruple, your instrument becomes a single quadruple mass spectrometer. And your system is a triple quadruple, means there are 3 quadruples inside. Then it becomes a triple quadruple system. And then the system is called GC-MS-MS or LC-MS-MS. It's a tandem mass spectrometer. Here it is a single quadruple MS. That's why we are writing SQ. So wherever you read SQ, it's a single quadruple system, and wherever you see TQ, it's a triple quadruple system. So we are discussing only a single quadruple system today. So this is a normal flow chart of a normal GC-MS system, irrespective of the brand. I'm not talking about any brand. I'm only talking about the technique. So the sample, you have a sample, different compounds are present. They have to be separated and identified. The sample has to go to GC column. And there is an arrow you can see, direct inlet. I will talk about later, not now. Initially, the sample has to go to GC column. Column will separate all the compounds, and one by one, the compounds will start coming out of the column. And when it comes out, it is going to enter the mass spectrometer. And the mass spectrometer has got 3 major parts. One is the ion source, mass filter or mass analyzer, and the detector. Okay. So the compound is going to enter the ion source. That's the place where the compound is coming, and that's the place where the compound is going to be ionized. Okay. Now this ion source, mass filter, and detector, they are all connected to a vacuum system. And what is the role of this vacuum system? We will see a slide going forward. So I will explain that. So initially the compound is coming to the ion source. And in ion source, the sample is going to be ionized. And how that is happening, you'll see. So your sample is going to be ionized, means sample is going to be broken down. for the students to understand in a much better way, suppose you have a glass bowl in your hand or a glass bottle in your hand, you just drop it down, it will hit the floor, and the bottle will be broken down into pieces. And when it is breaking down into pieces, not all pieces are the same. Some are very small pieces, some may be medium size, some may be larger pieces. Different types of different shape, different size of pieces will be formed, and each piece will be having a certain weight. Weights are not same. A small piece will be having a very low weight, and a bigger piece will be having a much higher weight. Similarly, when your molecule is getting broken down in the ion source, it is going to be splintered, it is going to be fragmented into pieces, fragments. And each fragment will be having a mass number. Like a glass piece having a certain weight, here the fragments of the original molecule will be having a certain mass number. So we are going to get different fragments of the original molecule having various mass numbers. And all these fragments are to be separated on the basis of that. And that is what is done by the mass filter or the mass analyzer, which is a quadrupole. That quadrupole is the mass filter here. That's why we call it as a quadrupole system. And the quadrupole, that is a mass filter, is going to separate all these fragments based on their mass number, and they are all taken to the detector. And the detector here is an EMT, is an electron multiplier tube, and the detector is going to give a signal, and the signal will be processed by your software, and then you get a printout. And when you get a printout, that is what is the output you are getting from a mass spectrometer is the mass spectrum. The mass spectrum is going to be the basis of identification of a compound, qualitative identification of a compound. And the mass spectrum is the output from the mass spectrometer. Now, there are different ionization methods in the case of GCMS. When you are buying an equipment, whether it is any ABC brand, any brand you buy, you will always get an electron impact ionization mode as by default method. And there is a very popular ionization method which is known as EI mode, electron impact ionization mode, or it is simply called EI mode. And that is by default you'll be getting. It's a very hard ionization technique, very high energy technique. And from the resulting mass spectrum, you can get a lot of structural information. You can go for a library search also. Then there is an optional method, which will not come by default. You have to separately take it. That's called a chemical ionization method. And chemical ionization method can be bifurcated into two types. One is called positive chemical ionization method, PCI, and negative chemical ionization method, NCI. Okay, and in general, chemical ionization is a slow ionization technique, whereas EI is a very hard ionization technique, CI is a very soft ionization technique, low energy technique. And we have two types. One is PCI, positive chemical ionization will give information about the molecular weight of the compound. So molecular weight of the compound information can be available from a positive. So if you want to find out the molecular weight of the compound in mass spectrometry, you can go for a positive chemical ionization mode of analysis to get molecular weight information. And when I have a sample in which I need to find out, I need to detect and quantify the extremely low concentration of an electrophilic sample. Remember what I told you about normal GC, where we are going to use an electron capture detector, which contains a radioactive isotope, extremely powerful for the detection of trace amounts of electrophilic compound. The same analysis I can carry out in the case of a MS with the help of a negative chemical ionization mode. I can analyze, I can quantify an extremely small concentration of an electrophilic sample using NCI mode. So there are, in fact, in total, we have three different types of ionization mode: electron capture, electron impact ionization mode. You can go for library search with that, so that you can identify the compound. Then we have chemical ionization, where you have two different types, PCI and NCI. PCI will give you molecular weight information, and NCI can be used for trace analysis of electrophilic compounds. This is actually what happens in the case of electron impact ionization, where the sample is coming out of the column and it's entering the ion source. Ion source contains two different filaments, and the one filament is heated. The filament at the top is heated. It is emitting electrons at a certain temperature, and the filament at the bottom is actually accelerating it. So the filament at the top is emitting electrons. It is a emitter, and the filament at the bottom is the collector, because it is actually accelerating. It's pulling the electrons down. And these electrons are thermal electrons with 70 electron volt energy. And normally for an organic compound, the ionization potential can be somewhere around, roughly around 15 to 20 electron volt. And now these electrons have 70 electron volt, so it's 3 to 4 times more energy. And when the sample is actually passing between these two filaments, these electrons are going to come and bombard it. And the bombardment is so heavy with 70 electrons, it's a huge quantum of energy with which these electrons are going to come and bombard the molecule. The molecule is going to be fragmented. And depending upon the structure of the compound, structure of the molecule, different fragments will be produced having various mass numbers. And these are subsequently separated by your quadrupole mass analyzer, will be taken to the detector, and the detector is going to give a output. That's a mass spectrum. And what you see at the bottom is the mass spectrum of methyl estrostearic acid. And if you look at very critically, this EA spectrum, this is a spectrum produced by electron impact ionization. And spectrum is very complex. So many fragments are produced. And for the students to understand, you will see different lines here. For example, there is a line at 74, line at 87, line at 140. Each line that represents a fragment. So 74 line means there is a fragment having a mass number 74. 87 line, so there is a fragment having mass number 87. And there's a fragment having mass number 143. So each line indicates the presence of a certain fragment having a certain mass number. So different lines, you can see different fragments are going to be formed, and electron impact ionization is a near total ionization technique. Near total ionization means the molecule is most likely to be fragmented totally. So nothing will remain of the original molecule, which will give an idea of the molecular weight. That's a problem. So that's why we are not able to find out exactly what is the molecular weight of a compound from an electron impact mass spectrum. At the same time, this mass spectrum can be used for library search, so that the compound, the library will tell you this is methyl stearate. The library, of course, it gives a list of compounds in the probability order. So it is going to identify the compound. So this spectrum can be used for finding out qualitatively what is the compound. You can go for a library search. Okay. But molecular weight information, most of the time it is not available. But sometimes you can get, so for example, here, if you critically see at the extreme right-hand side corner, there's a very, very small fragment which is shown as 298. It's a very extremely small, tiny fragment, you can say 298. But we are not sure whether it is a molecular ion. We do not know. So if you want to find out the molecular weight, we have to analyze the same compound under PCA mode, positive chemical ionization mode. That will clearly tell us what could be the molecular weight of the compound. Now we are coming to positive chemical ionization. Now, in the case of GCMS, I told you we are going to use only one gas. That is a carrier gas, that is going to be helium. Helium is the ultra pure helium is the carrier gas that we are using in GCMS analysis. Okay, no other gas is required. But when we are having a positive chemical ionization mode of analysis, we also require a reagent gas. Carrier gas is there, helium, that is there. Other than that, we require a reagent gas to carry out a PCA analysis. And there are three different types of reagent gases that can be used. One is, all these are ultra pure gases: methane, isobutane, and ammonia. These three gases can be used. But most of the time, very popular reagent gas is methane. So what we normally do, we introduce a very small amount of the reagent gas into the ion source. And this reagent gas will be bombarded by the electrons, normal thermal electrons, and these reagent gases will undergo some fragmentation process, and it will produce some plasma ions, it will produce some reagent ions. And these reagent ions are by and large unstable. Their tendency is always to go back to a stable form. Now, having achieved this, we are introducing our sample. And when the sample comes to the ion source, these reagent gases, reagent ions produced from our reagent gas, that is methane, will have a secondary collision with the sample molecule. And thereby, the sample molecule will get an additional proton and these reagent ions will go to a much stabler form. Okay, that we will see what this is. So for example, you can see methane, we are going to use methane as the reagent gas. So when methane is used, methane will undergo ionization first, and then it will produce certain reagent ions which are unstable like C2H5 plus and CH5 plus. Okay, and the tendency is always to go back to a more stable form. So when the sample molecule is coming, that is M, and we are denoting our sample molecule as M. And when it is coming, these reagent gases will go and collide with the sample molecule. In that process, the collision energy is of much lower side. And C2H5, when it is colliding with M, then additional proton in C2H5 plus will be given to the sample molecule. C2H5 plus will become C2H4. It's a very stable compound. And the molecule, our molecule has received an additional proton, so it will become M plus H or M plus 1. Okay, so if you look at the mass spectrum, what you see here at the bottom is the mass spectrum of methyl stearate, the same compound we have seen under EA also. But here you are seeing a very clean spectrum. Not many fragments are formed because it's a low energy collision. And if you look at the extreme right hand side, you will find a very strong fragment which is coming at 299, because methyl stearate molecular weight is 298. So when it has undergone a protonation reaction like M plus H, molecular weight is going up by 1 unit, that is 299 plus 1, it has become 299. So you can see a very prominent fragment, very strong fragment at 299 minus 1, that is the molecular weight of the compound. So you can get a very easily find out what is the molecular weight of a compound. Now, positive chemical ionization, the gas phase analytes can undergo 4 different types of reaction with the reagent ions. Now here the reagent is our methane is the reagent gas. It should be noted that only charge transfer results in the formation of M plus or molecular ion, and the rest of the reaction mechanisms generate quasi-molecular ion. So when we are using methane as the reagent gas, the most prominent plasma ions are CH5 plus and C2H5 plus. Others are formed in very low concentration like CS3 plus, C3H5 plus, C5H11 plus. They are all very low concentration, but most prominent reagent ions will be CH5 plus and C2H5 plus. The reactions you can see here, first electron ionization of methane, CH4 gets converted to CH4 plus, and the second ion molecule reactions creates stable reagent ions plus CH4. It can give you CH5 plus, and CS3 plus CH4 it can give C2H5. And these reagent ions can collide with the sample, and it is something like a protonation reaction. The proton is given to the sample, and these reagent ions will go back to a stable form. And there are typical ion molecular reactions or pieces like charge transfer is the, proton transfer is the, hydride transfer is the, collision stabilized complexes are can be formed. Now, if you compare the, we have a sample, we have analyzed it by EA mode and CA mode. Look at the spectra. The top one is under EA mode. The same sample is analyzed by PCA mode. You can look at the spectrum at the bottom. So one, you can see the EA spectrum is very complex compared to CA spectrum. Okay, EA spectrum can be used for library search for qualitative identification, and CA spectrum can be used for identifying the molecular weight of the compound. Okay, the strongest peak in the PCA spectrum is an M+1 peak, and the strongest peak in the EA spectrum is always a base peak. Base peak is the basis for basically when you are going for a library search, the first of what is identified is the base peak that is coming from the compound. So the EA model spectrum of the sample, the base peak is 125. Okay, now whereas in the case of PCI, the strongest peak is at 331. That's a M+1 peak. So when you are, so please understand, if you want to do a qualitative analysis, you have to analyze the sample only under electron impact mode, so that you have the freedom to go for a library search and find out what is the compound qualitatively. Never ever do a qualitative library search using PCA mode. That will give you some wrong result. library search should be carried out only with EI mode of analysis. Similarly, we have got negative chemical ionization mode, negative ion formation. Here we are going to capture negative ions, not positive ions. And negative ions formation can be by electron capture. There are different methods: associative resonance capture, dissociative resonance capture, ion pair production. Similarly, ion molecular reactions can take place for proton transfer, charge exchange, nucleophilic addition, nucleophilic displacement. Different types of reactions can take place. We are not going to those details. Negative ion formation by electron capture. The compound, suppose the sample, whatever you are analyzing is an electrophilic sample. Especially at very, very low concentration, it has affinity for electrons. It can capture electron and provide you a negative ion, and that can be captured. And there are different types of associative electron attachment, dissociative electron attachment, ion pair formation, depending upon the energy of the electron that is coming and bombarding with the sample molecule. We are coming to the second part of the mass spectrometer, that's a mass analyzer. Now we have done with ion source. Now we are coming to the mass analyzer or the mass filter. And what is a mass analyzer? It is an integral part of your system, of your equipment, which is responsible for the separation of the ions produced in the ion source on the base of mass number. I told you when the sample molecule is coming out of the column, it enters the ion source, it undergoes fragmentation because of the electron impact, and different fragments of the original molecule will be formed having various masses. So you are getting a mixture. As the example I gave you, when the glass bottle is broken down, you are getting different pieces having different weights. So here also you are getting different fragments. So an ion source contains different fragments of the original molecule having various mass numbers. And they are separated on the base of their mass number by the mass analyzer. So what is different mass filters are available? Magnetic sector is there, quadrupole is there, time of flight is there, ion trap is there. So these are different types of mass filters. But one of the popular mass filter today, which is widely used in industry also, is a quadrupole system. So what you see on the left-hand side is ion source. The sample, the compound has come eluted out of the column. It came here, it has undergone fragmentation, producing different fragments having various mass numbers. And in the middle, what you see is that written as Q, that's a quadrupole. It is going to separate these fragments on the base of mass number. And on the extreme right-hand side, what you see is the electron multiplier 2 that is going to give the signal. So this is a quadrupole system. The name itself, you can understand there are four rods. That's why it's known as quadrupoles. 4 rods are there, cylindrical rods. And they are arranged in such a way that 2 rods, one is at the top, one is at the bottom, and 2 rods are sideways. So that's arrangement. Okay. So what we normally do, we are applying a DC voltage across one pair and a radio frequency across another pair. So at any point of time, there is a certain ratio of DC to RF. And for a certain DC to RF ratio, one fragment from the ion source will come out. It will have a very stable trajectory and it will pass through the distance between the free space between the quadrupoles, and it will go and touch the detector. That means we are successful in extracting one fragment from the ion source and sending it to the detector. So like that, our aim is to take out all the fragments. So what we do, we keep on changing this ratio and thereby taking out, extracting all the ions from the ion source and sending them to the detector. And this has to take place in in a very, very short period of time, because if all these fragments are not removed from the ion source in the proper period of time, second compound will come out of the column. That also will come to the ion source. That will also undergo fragmentation. There will be a lot of mix-up. So that should never happen. So before the second compound comes, all the fragments produced in the first compound will be removed and taken to the detector, and the detector is going to give an output which is the mass spectrum of that compound. And the second compound will come and that process will continue till all the compounds are coming out of the column. Okay, that way you are getting, so one compound for each compound, you are getting a mass spectrum. So if you are going, the sample contains 10 different compounds. So all these 10 different compounds will produce 10 different mass spectra. And the mass spectra can be used for the identification. Capabilities of a quadrupole system, it can carry out excellent qualitative analysis for a multi-component sample. Today we talk about a lot of multi-component samples like pesticide residues. multi-components. So many components are present in a sample. Perfumery system, environmental samples. I mean, we are talking about different numbers. So many number of components in a given sample. It's a multi-component system. So it can carry out excellent qualitative analysis. Can provide very reliable library search data. That is one of the major advantage of using a quadruple system. It can provide very reliable library search results, and it also has got good quantification capability and easy to use. There are two different modes of analysis in GCMS. One is known as a scan mode and one is known as a SIM mode. So please keep in mind, scan mode is to be used for qualitative analysis and SIM mode is to be used for quantitative analysis. That's a very simple. You have two different modes for two different objectives. One is your qualitative analysis. You want to know what are the compounds. You want to identify the compounds. Go for a scan mode. And after that, if you want to find out what is the concentration of each compound, quantification, come to SIM mode. That's all. Okay, now what scan mode? When you are having a scan mode of operation, you have to set a range of mass number, starting mass number range and ending mass number range. For example, many times we start from 40 AMU and then we go to 400 AMU. I mean, just giving an example, that's all. See, that means from 40 is the starting AMU range and it is going up to 400. So that's a range. Starting range and ending range, 40 AMU and 400 AMU. So when the sample undergoes fragmentation, whatever fragments are going to be produced for the sample molecule, which are in between 40 and 400 AMU, all those fragments will be seen by the detector. Detector will see each and every fragment which are falling between 40 AMU and 400 AMU. So, and it is used for qualitative analysis. So scanning is performed continuously at a regular interval from a lower mass number to higher mass number. That's why I told you, like 40 to 400. And all the fragments will be seen by the detector. And then this spectrum, whatever the spectrum you are going to get by doing the analysis in the scan mode, and that spectrum should be utilized for your library search. Because we cannot omit any fragment. All the fragments should be seen by the detector within the given range, and that spectrum only can be used for the library search. That is identification. Okay, now you got an identity. You have identified the compound precisely. Now you want to know what is the concentration of that compound. You want to do a quantitative analysis. You're going for SIM mode of operation. SIM stands for selected ion monitoring. So selected ion monitoring means when a sample is undergoing fragmentation, it may give you many fragments depending on the structure. You can give 10 fragments, 15 fragments, 20 fragments or more also. But you are not interested in seeing all those fragments. You are only interested in maybe 4 or 5 or 6 different intense fragments. You can select. I mean, there is a lot. I mean, so we can select 4 or 5. You can select more also if you want, then no problem. But then you are only looking at certain intense fragments. So you have to select it. That's why selected ion monitoring. So for example, my sample is giving me 15 fragments. And out of these 15 fragments, there are 3 prominent or 4 prominent fragments. I'll be selecting those prominent fragments. And these fragments I'll be feeding in my software. Okay. Now it is used for quantitative analysis. Okay, in this mode, only the selected ions or the sample molecule will be monitored by the detector and more sensitive than scan mode. So quantification by SIM mode is always more sensitive. In scan mode also, if you want to do, you can do a quantification but the sensitivity will not be very good. So if at all you want to do a quantification, please do the quantification in SIM mode. I can just show you an example. Here is an example of SIM mode of operation. A certain sample has given multiple fragments. And out of these multiple fragments, 3 prominent fragments were selected, 54, 72, 152. So when I am giving these 3 fragments, the software is making actually 3 different compartments. One for 54, second one for 72, third one for 52. And each compartment, the ratio DC to RF ratio is fixed. So we are keeping a ratio which can see only 54 in the first compartment. We are keeping a different ratio which can monitor only 70 to the second compartment. And we are fixing the ratio which can see only 150 to the third compartment. So there are three different DCRF ratios are fixed, each one for each of the selected fragments. So when other fragments are coming, the ratios are not there, they will be totally blank. So the detector will be able to monitor these three selected fragments, and based on this, you can get a very high accurate quantitative result. So SIM mode is to be used for quantitation and scan mode is to be used for qualitative analysis. Now, why vacuum is important in MS? I told you vacuum because in the case of GCMS, your ion source, your mass filter, and your detector, they're all connected to a very powerful vacuum pump. In the case of GCMS, there are two types of vacuum systems, two types of vacuum pumps. One is known as a rotary pump, rotary vacuum pump. That's actually kept outside the system. It's below your table. On the table, you are keeping a GCMS system, and below the table, you can keep a rotary. The rotary pump is designed to give a certain initial vacuum, what normally we call it as pre-vacuum. And then the final vacuum, which can go to the tune of 10 to the power of -5 to -6 torr, that is created by a vacuum pump which is kept inside the equipment. That's called a TMP, turbomolecular pump. Turbomolecular pump, I mean, it has got blades, it will rotate at a very, very fast speed. So normally, you cannot start with the turbomolecular pump because of the friction of the air inside. The blades can go bad. So that is the problem. So it can get, the TMP can get spoiled. So initially you have to create a pre-vacuum, which is normally to a tune of 10 to the power of -2 to -3 torr, and that is what is achieved by the rotary pump. And having got this pre-vacuum, the TMP can be started, and then the final vacuum will be achieved. There is an auto start. I mean, nowadays there are a lot of functions. All this starting up of the instrument, all can be done automatically. But vacuum is a very important factor, because why vacuum is important? When you are shutting down the equipment, any vacuum system, when you are breaking the vacuum, external air will be sucked inside. And that means if you are shutting down your GCMS system, air will go inside the ion source in the system, MS system. Air means nitrogen will be there, water vapor will be there, oxygen will be there, all this will be there. Now tomorrow morning you are coming and starting the equipment without removing this air. What will happen when the sample undergoes fragmentation? The sample fragments will go and collide with these gases. It can collide with water vapor, it can collide with nitrogen. And if this type of collision takes place, there will be a very big, very great background noise production. That means subsequently your signal sensitivity will be extremely poor. So that should not happen. So vacuum is applied to pump out the residual gases like air and water vapor and all from the system. And once you are removing this, prevents the chances of collision of the sample ions produced and the residual gases, which otherwise may produce very high background, reducing the sensitivity. So vacuum creation is a very important factor. Don't overlook the importance of vacuum. So once you have start the equipment, you have to start the vacuum, you have to get the final vacuum, you have to get a stable vacuum. There is something called good vacuum and clean vacuum and all. And you have to keep the instrument running for quite some time. And allow the vacuum to stabilize. You monitor the baseline, and then you start with a very, very sensitive analysis. A good vacuum reduces noise level, and at the same time it improves sensitivity. So vacuum is a very, very important function. Then variable ionization voltage, normally I'm not going into these details because these are all basically your software functions. Normally the electron impact ionization, the electrons are normally coming out to 70 electron volt, and the user has got freedom to change this electron volt. From 70 electron volt, you can change it. You can increase or decrease. So depending upon if you are trying to decrease the electron volt, there is a possibility that you can see a molecular ion very clearly, which will give you an information about the molecular weight of the compound. So even though you are not having a PCI facility, by using this function variable ionization voltage, sometime you can get an information as to what could be the molecular weight of the compound. But I am not telling that this is a replacement of PCI. No, this is only a software function that is given to the user. Don't think that with this function you can get rid of PCI if you want an exact molecular weight. No, it's not like that. This is a function. So for example, here 70 electron volt energy, that is by default in the case of. So you have a compound and 70 electron volt. When the electrons are bombarding the sample is going to be fragmented, and possibly you are not able to see the molecular ion peak, or even if it is there, it is such a very small ion, you are not very sure whether it is a molecular ion or not, or it can be a noise signal. You reduce the electron volts. So from 70 you come to 40, and your observation is that M plus ion intensity is increasing. That's a molecular ion that is increasing. Come down further, from 40 you come to 20 electron volt. You can see the M plus ion intensity is still enhanced. So that means you are able to identify the molecular ion by making use of this variable ionization voltage. That's a facility which almost all the instruments are giving. And how to find the compound in terms of I told you most of the case of, in the case of a non-conventional GC, your retention time is the basis for identification of your compound. But that is not a foolproof method, because retention time is always condition dependent. If you change the condition, the retention time can change. There is another factor which is known as retention index. Retention index of a compound on a given stationary phase is always constant, irrespective of the condition. So that is that because of this, a retention index becomes a more authentic basis for identify the compound, rather than trying to identify the compound based on retention time. And what is the retention index? How do you find out? Because for retention index determination, you have to use a certain standard. These are all N-alkane standards, saturated hydrocarbons, say from C7 to C33. And all these are saturated hydrocarbons. They can be separated by a nonpolar column under a certain set of conditions. And you get beautiful separation of all these hydrocarbon peaks, like for example, C20, C21, C22. Like that, you can get all those alkanes separated. Now, by convention, the retention index of a saturated paraffin, saturated hydrocarbon, alkane, N-alkane, is carbon number multiplied by 100. That means C20, the carbon number is 20. If you multiply by 100, it becomes 2000. So retention index is 2000. C21, it is 2100. C22 is 2200. Okay, carbon number multiplied by 100. Now, if I'm injecting it in my sample, and if my sample peak is coming, for example, here it's shown as an example, coming between C21 and C22. And C21, you know, retention index is 2100, 22 is 2200. My sample compound has come in between. So by logic, you know, the retention index should be between 2100 and 2200. And how it is exactly found out? So what the software will do, the distance between 21 and 22 peaks are divided into 100 equal segments. And then it will count on which segment your compound is coming. Our compound is coming on the 42nd division. So the retention index is 2100 plus 42, it is 2142. This retention index will remain same on the same stationary phase, irrespective of the conditions. If you change the conditions, your retention time can change, but your retention index will not change. Okay. So you can see here, even if you are maybe slightly cutting the column length is reduced for certain reasons, column cutting, I'm not going to those intricacies. So there can retention time may change. Okay, my retention time, initially it was coming at a certain time, now it is reduced. I mean, it's coming at a different time, but my retention index will never change. So that becomes a very, very easy way of finding out the compound, irrespective, even if there is a change in the retention time, you can optimize it and you can identify the compound without any problem. Okay, now fast GCMS, I told you when I talked about the 4 S values, and the third S value, all the students will be remembering the analysis time. Okay, first S was sensitivity, selectivity, and the time of analysis. Okay, so but now by using a fast analysis technique in GCMS, we can actually reduce the analysis time. Example also I told you, suppose if I am having a certain sample which takes about 50 minutes to complete or 60 minutes to complete, if I'm able to reduce it to 20 minutes or less than that, I'll be able to analyze 4 samples in the same time. That means initially it was taking 1 hour, now it is taking 20 minutes, that means 1 hour I can analyze 4 samples. So I'm increasing my output. So for this carrying out this fast analysis, there are certain hardware requirements also. Your column oven should have a very, very high heating rate. Your carrier gas column head pressure will be very high. You should have a very high split ratio because we are using a microbore column here, microbore capillary column here, having an internal diameter of 0.1 millimeter. And you require a high pressure to send a sample inside and a high MS scan rate. So these are some of the requirements. And with this, we can actually carry out a high-speed analysis. For example, there's a perfumery compound. There are two spectra TSC shown, one at the top and one at the bottom. The top one is a normal GCMS. It's a perfumery compound. So many compounds are coming from the sample. And it has taken approximately 50 minutes, more than 50 minutes for the run to complete. Approximately 1 hour. The same sample is analyzed under fast mode of analysis, and the analysis getting completed in less than 10 minutes time. That means in 1 hour time, I'll be able to analyze at least five compounds, 5 samples. That means I'm increasing my output by fivefold. So then we are not compromising on the resolution. We can see the resolution by normal GCMS and resolution by fast GCMS. We don't compromise on the resolution. We are only trying to reduce the analysis time, thereby increasing the output. And which is, I told you earlier, this is the output. That's a requirement of the day in the corporate world. And there is, if you actually remember the flow chart, what I showed you in the beginning, I showed the sample has to go to GC. And at the same time, you also saw an arrow, the sample going to the MS. And I told you I'll talk about this later. So I'm coming to that point. We have a probe. It's called a direct inert probe, DIP, with which a sample can be directly introduced into the mass in the mass spectrometer without introducing to the column. But where it is applicable, suppose your sample is a very clean sample, it's a single sample, like in the case of pharmaceutical analysis, many of the pharmaceutical drugs are single compounds, purified compounds, and I can introduce this. There is no impurities to be separated, nothing. I can put the sample into my mass spectrometer using a probe. And the probe is very small, I mean, it's very convenient to use. And you have to put a very extremely small quantity of the sample in a small quartz cup. And the quartz cup will sit in front of this probe, and this probe can be pushed into the mass spectrometer without affecting the vacuum. And what is the plus point? You can complete the analysis within very, very short period of time, less than maybe 5 minutes, 6 minutes, 7 minutes, you can complete. This analysis of reserpine is a anti-BPA drug and having a high molecular weight, and normally may not be possible by a direct column injection, because many times some steroids and other things we cannot directly inject into the column without derivatization. We go for a TMS derivative preparation for steroids and all. But here we are doing a DIMS analysis. We are not doing a GCMS analysis. We are doing a DIMS analysis. Directly putting the sample into the MS, and we can get a fragmentation pattern. We can go for library search, all those we can do. And last part of this presentation, we are coming to some of the important applications. What are the fields? A lot of areas where we can use GCMS: pharmaceuticals, pesticides, perfumery, foods, petroleum industry, polymer industry, environmental samples, biomedical applications, forensic applications, spices and essential oils, textile applications, ROS, biofuels and biotechnology. A lot of areas where we can use AGCMS for wonderful applications. Number one in the pharmaceuticals, for residual solvents in API, every pharmacy student know, because most of the students are, I think, pharmacy students. Now, the residual solvent analysis is a very, very important analysis in pharmaceutical industry, API manufacturing. You have to do this as per USP method number 467. If you read method number 467, there's a whole method available for determination of residual solvents. Once upon a time, it was called OVI, organic volatile impurities. But now the nomenclature is changed. We call it as residual solvents. And the method number is 467. USP, you can refer that. And in 467, there are 3 different procedures given. Procedure A for separation, procedure B for identification, confirmation. Procedure A for identification, procedure B for confirmation, and procedure C for quantification. where 3 different columns are used and 3 different conditions. So those details are there in method number 467, where we have to use a GC along with a headspace attachment. We cannot directly use GC or GCMS. We need an attachment called a headspace attachment, which is to be connected. It's an accessory for GC or GCMS and should be connected to the system. And then I'll show an example. Identification of intermediates in API, impurity profiling of finished API, analysis of raw materials, molecular weight of pure drugs. Lot of applications are there for GCMS in pharmaceutical industry. This is an example of a headspace analysis. Headspace analysis is nothing but a sample introduction system. It's an injection technique. Simple definition is analysis of a volatile component in a non-volatile matrix. Your sample is non-volatile. It contains a volatile material. So how to identify that? How to analyze that? You can go for a simple example. I can tell you for easy understanding. It's a forensic application. Alcohol in blood. When people consume alcohol, it will after some time it will come into the bloodstream. So if I take out a small quantity of blood, and I cannot directly inject alcohol is nothing but your ethyl alcohol. So you can get ethyl alcohol is highly volatile material. Blood is a totally non-volatile. It's a biological fluid. It's a non-volatile material. If I inject a small quantity of directly into my GC column, my column will be spoiled. It will be clogged. It will be spoiled. It can contaminate my injection system. So a lot of problems. So I cannot directly inject a blood sample, any biological fluid into my GC column directly. At the same time, I want to find out ethyl alcohol content in blood. Then I go for a GCM. I go for a headspace system. So headspace is nothing but analysis of a volatile component in a non-volatile matrix. So this is a typical example I told you. So what we do, we take a small quantity of sample. It can be a liquid sample. It can be a solid sample in a 22 ml vial. That's a normal standard vial we use in headspace, 22 ml thick walled glass vial. We take a small quantity. If a liquid sample, maybe 1 or 2 ml of sample liquid will be more than sufficient. For example, in this case, a blood sample. 2 ml of blood is more than sufficient. And the total volume is 22 ml of the glass vial. You seal it with a septum and aluminum cap and make it completely leak proof. You have to crimp it and you have to put it in a small oven in the headspace attachment. And then you are going to heat it. You have to optimize the temperature. You have to optimize the time, the incubation temperature, incubation time and all. So what will happen when you heat in the sample, say for example, blood sample, ethyl alcohol will evaporate. Alcohol will vaporize because it's non-volatile. It's a volatile component, but nothing will happen to blood. So that alcohol vapor will accumulate inside the glass bottle because it cannot escape because the bottle is totally sealed. And then there will be an equilibrium established. And after that, there are 2 ways of taking this vapor and sending it to the GC column. One way is called a gas-tight syringe. A syringe will come, automatically pierce the septum, rubber septum, and take out a certain quantity of the vapor which you have already decided. You have to feed how much vapor is to be taken. Say 1 ml. So it will take exactly whatever you have told, that 1 ml of vapor it will take, and then it will go back and go to the GC injection port and inject the sample into the GC. So what is the advantage? You have only injected clean vapor of the sample into the GC column, whereas blood will remain in the bottle. Blood is not going into the column. Only the alcohol vapor is going into the column. And that means your column is not getting contaminated. Your injection port is not getting contaminated. Column life will be enhanced and your analysis will be much faster also because you are not introducing any non-volatile impurities in the sample, into the column. So that is a wonderful way of analyzing. So this is called a gas-tight syringe method. And there is another method which we now totally pharmaceutical industry. This method is not used. The vapor can be transferred from the bottle to the column with the help of a capillary tube. That's known as a capillary tube method. Here, this is called a syringe method. And this equipment is available. We have this equipment where we can use a gas-tight syringe. And we also have another equipment which uses a capillary tube transfer mechanism. This is known as a transfer line mechanism. We are transferring a certain quantity of vapor from the bottle to the column with the help of a transfer line. It's known as a transfer line mechanism. So we have a headspace sampler, which is called HS20. It's a very popular headspace sampler. This can be attached to GC. This can be attached to GCMS, or this can be attached to GCMS also. So this is a way of, and lot of applications. Not only in pharmaceutical industry, lot of other areas also it has got, headspace injection has got lot of applications. This is a typical example of residual solvents in API, class 1 solvents. All pharmacy students know there are three. The USP has classified the solvents into 3 different classes: class 1, class 2, class 3. Class 1 solvents are the most carcinogenic solvents. As far as possible, they should not be used in the preparation. And what are those 5 solvents? Extremely carcinogenic solvents. Number 1 is 1,1-dichloroethene, 1,1,1-trichloroethane. Third one is carbon tetrachloride. Fourth one is benzene. And last one is 1,2-dichloroethane. Okay, so there are limits also. Class 1 solvents are the most dangerous solvents. Then we have class 2 solvents, where it is it is much less carcinogenic. The limits are more relaxed in the case of class 2 solvents. So class 1 solvents and class 2 solvents are to be analyzed by GC or GCMS, and of course with the help of a headspace sampler. And then the least dangerous solvent, they are classified into class 3 solvents. Normally they are determined by loss on drying, LOD, not by chromatography. They are determined by loss on drying. So this is an example of a separation of class 1 solvents. All the 5 solvents, you can see they are very well separated using a RXI 624 SIL-MS column. DB 624, RXI 624, basically is a 6% cyanopropyl modified 94% dimethyl polysiloxane column. It's a wonderful column for separation of different compounds. It's a medium polar column. And the column length was 30 meter. The diameter of the tubing was 0.32 millimeter. And the thickness of the film, the stationary phase thickness was 1.8 micron. That was the thickness. Then this is a CA spectrum of a drug, a certain and is a pharmaceutical drug analyzed by CA mode of analysis. And you can clearly find out what is the molecular weight. From the CA spectrum, you can get an information as to what is the molecular weight of the drug. It's 207. It's very, very simple. And here is an example of DIMS analysis, not MS, DIMS analysis. We are analyzing certain, say for example, I'm analyzing a steroid, prednisolone. Steroids can be analyzed by GC or GCMS. If I want to inject into column, I have to prepare a TMS derivative, trimethyl-silyl etherification reaction with BSTA pyridine medium. We have to prepare a TMS derivative, and then we have to inject into column. So it is time consuming. BSTF reagent is very costly and takes time also. But whereas here, nothing, no derivative, directly we are injecting the steroid into MS with the help of a DA probe. Similarly, the next one you can see reserpine. So there are samples which can be directly, but provided these samples are very clean samples. And this is a herbal drug. Normally, herbal drugs are very difficult to be analyzed by GC column unless there goes some derivatives and react, because they are highly polar samples. Very difficult to come out. A lot of tailing, a lot of difficulties will be there. You have to convert to suitable derivatives before injecting into column, but we can use a DIMS for that. Genotoxic impurities in pharmaceutical manufacturing. API manufacturing is a chemical manufacturing process. Different impurities are getting formed. For example, this methane sulfonic acid esters are considered as genotoxic impurities. See, some examples are methane sulfonic acid ester, benzene sulfonic acid ester, paratoluene sulfonic acid ester. These are all basically sulfonic acid esters. They are considered as genotoxic impurities in pharmaceutical API manufacturing. And these are to be precisely controlled and quantified because there are limits for that. Genotoxic, otherwise these are genotoxic impurities. You can use a GCMS for that. I mean, this is a separation of almost around 10 to 12 different types of sulfonic acid esters using a certain column. So you can get any, and then with the help of standards, you can precisely quantify them. Another type of genotoxic impurities, alkyl halides. You also can see around 18 to 19 different types of alkyl halides are separated. And then with the help of standards, you can even go for quantification. One of the latest requirement in pharmaceutical industry is the presence of nitrosamines in drugs. Recently, you must have read, I mean, it's a major topic of discussion. Certain group of drugs will containing different nitrosamines, NDMA, NDA, different nitrosamines, highly carcinogenic compounds. And so many, you must have read, different manufacturers have recalled their batches on the market. And because of the presence of nitrosamine, there are about 6 or 7 nitrosamines possible. And these are 2 examples, NDMA and NDA. And they can be precisely analyzed, identified, and quantified with the help of a GCMS and using a headspace analyzer. So you can see the multiple standards and how we are quantifying and quantification. And this is an overlay of standards prepared from 2.5 ppb to 10 ppb. Okay, that's basically the quantification process. GCMS in biomedicals. This is again an upcoming area where you can find out metabolic disorders in newborn children with the help of a GCMS system. Neonatal, NBS, newborn screening, of course, it is not as mandatory place. But if a child is screened for any possible metabolic disorders, and the physician can decide the treatment to be given started at a very early age, so that many of the unpleasant problems will not occur. So GCMS is a very important tool in neonatal screening for metabolic disorders. And what is the starting material? The starting material is urine collected from the patient, collected from the child. And the urine that is coming out of the human body contains a lot of carboxylic acid by way of different metabolic reaction that is taking place inside. And any human, any healthy human being, there is a certain carboxylic acid profile. But if there is a problem, there is any disorder, this profile will change, and the change in profile will indicate a certain disease. So that is what is that. So the urine sample is to be collected from the patient, and urine is a biological liquid. It contains a lot of unwanted metallizers. So they are to be the urine is to be extracted for the carboxylic acid. They are to be cleaned up, and finally they are to be derivatized, and then that is to be injected into a GCMS system for the presence of carboxylic acid. We also have a certain software for that, IM software, inborn errors of metabolism software. With the help of the software, we can identify some of the disorders, and then ultimately it is left to the physician to decide the line of treatment. So this is a typical example of a urine sample collected from the child, and the carboxylic acids are extracted and cleaned up and derivatized and injected into GCMS. This is the profile of carboxylic acid profile of the urine sample. And then you can apply the software, then we can get a lot of information from that. GCMS in food industry, you can have a lot of applications food industry today. Flavoring compounds, there are a lot of flavored foods available in the market. I mean, when you go, you can pineapple flavor, orange flavor, these are all synthetic, are not natural flavors. They're adding a lot of synthetic chemicals. Then you can find out what are those synthetic flavoring compounds by probably use a GCMS with a headspace sampler also. Identification and estimation of residual pesticides, which is a global problem today. All pesticides are present in foods, whatever vegetables and fruits and marine products and meat, whatever we eat and whatever we drink, they all contain pesticide residues today. There are limits available. There are a lot of stringent regulations. And that is a burning topic today globally, identification and estimation of residual pesticides in food products. And you can do it by GCMS, MSMS, you can do it by LCMS-MS, GCMS-MS and all. Determination of residual solvents in packaging material. Packaging material also contains, these are all polymeric packaging material. They may contain some residual solvents. We need to identify and quantify them. This is an important application in pharmaceutical industry also. And coffee aroma. It's a food product, food application. Coffee has got a certain aroma. Firstly, I'm not talking about the synthetic like Nescafe. I mean, if you plug the coffee beans, the seeds, and then crush it, and then you make a coffee out of that, it has got a certain aroma. And this aroma can be different depending upon different conditions. What is the climatic conditions where the coffee plants were grown? the temperature, humidity, the soil condition, lot of things will affect the. So from a coffee plant grown in one place and coffee plant grown in a different location, the aromas can be different because there are a lot of different flavoring compounds are present in coffee aroma and be captured by another technique known as SPME. SPME stands for solid phase micro extraction. Again, you have to take the sample in a bottle and seal it and heat it, and you have to introduce a probe into this bottle, and this probe will actually absorb the coffee. Aroma products are all basically volatile compounds, and they will be absorbed by the probe, and then subsequently this probe can be introduced in the injected pot of the GC, which is a heated injector pot, and whatever is absorbed on the probe will get dissolved and it will go to the column, and we can have a very wonderful analysis of different types of compounds present in coffee powder, coffee aroma. You can see so lot different types of, and just giving few examples, different types of samples of compounds are present. Some are esters, some are aldehydes, some are ketones. Different types of compounds are present in coffee aroma, and this can be identified, and different types of coffee products can be classified also. And this is an example of pesticides in food products by GCMS. You can see so many number of pesticides can be separated by, and more number. These are just an example. It's about 59, 60 pesticides are separated. We can, in fact, separate much more number of pesticides residues in food products. But sample preparation is very critical. We have to extract the sample, and then sometimes we have to clean up the sample. The different procedures are available for that. And finally, we have to analyze the sample by GCMS or GCMS-MS or LCMS-MS. And then you can quantify all this also. It's a very, very important application in food industry. GCMS in forensic application. The most important application of GCMS in forensic science is the identification of drugs of abuse. I mean, even you must have heard of people taking part in athletics and all, with Olympic Games and Commonwealth Games. People take steroid injection to boost their efficiency. And ultimately, these drugs will come into your bloodstream, and a small sample of your blood tested for the presence of these steroids. I mean, that's very basically known as a doping test, and the person can get even disqualified also if the presence of steroid is established. It's a very, very sensitive test where we use GCMS-MS or even LCMS-MS. Analysis of poisonous compounds from a site of crime or even a dead person. Then alcohol in blood, all those are a lot of forensic applications are there. This is a typical analysis of blood alcohol using a GCMS and with a headspace. It's a typical forensic application. You can even quantify also. ROS application. ROS means restriction of hazardous substances. Many different carcinogenic compounds can be present in some of the toys and plastic materials, electronic items and all. These are all banned items. Many times these will be having different isomers also. For example, pentabromo-diphenyl ethers, a highly carcinogenic compound having various isomers. They are present in some of the electronic items and toys, or people, children are playing with the toys, they put it in the mouth, and these are all health hazards. So there are a lot of applications. You can use GCMS, you can use a energy dispersive X-ray fluorescence spectrophotometer for that. But GCMS also can separate all these different types of isomers. And this is a typical ROS application. And perfumery industry, perfumery compounds are extremely complex compounds. A 0.2 microliter of a perfumery oil injected into a high resolution capillary column, you can see how many peaks are coming. More than 100 peaks are coming from the compound, that from the sample. So that means the perfumery sample, the perfume what you are using on your body, on your fabric, is a mixture of more than 100 different chemical compounds. They can be separated only by a high resolution capillary column. And they can be identified only by a mass spectrometer using a suitable mass spectral library. Libraries are available, perfumery libraries are available today, and you can go. Otherwise, a normal GC cannot identify all these. It can only give you a chromatogram, nothing else. But when it comes to GCMS, it can identify also. That's the power of GCMS as compared to a conventional GC. and you are having different types of sample matrices. Some of the samples are of biological origin, like blood sample, urine sample, hair samples, or samples are plant origin, and some are non-biological origin, like pharmaceutical samples, forensic samples, toxicology samples, food samples, chemical samples. There is a long list. So we have applications for all these segments for GCMS, and depending upon the type of sample. So what are things to be, this thing is, you have to, first of all, you have to get a clean separation of all the compounds of the sample. There, I am again underlying the importance of column selection. Select the column, optimize the conditions, get a proper separation, and then MS will be able to identify the compounds, and you get a total identification of the compounds present in the sample. And having standards with you, you can even go for quantification. So that is and this is the last slide. And this is the latest single quadrupole GCMS on schematics called GCMS QP2020NS, a very, very powerful single quadrupole system. We also had triple quadrupole system, but I am showing only the single quadrupole system here. This is the latest system available in the market, QP2020NX. So with this, the last slide is my information. My email ID is given and my mobile number is given. So any other participant in going forward, anyone wants to contact me for more information, you are always welcome. Either you can contact me on my mobile or you can contact me on my email. Just give a reference from where, from which institution you are and what are you currently doing. A little background about your problem and about yourself will be beneficial for me to give a meaningful answer. With this, I'm ending my presentation. I think today I am on time. Over to you, sir.
Thank you, sir.
Hello.
Yeah, there is some question in the chat box, and there is some.
You can read it out.
Huh?
You can read it out. I'll answer.
Okay.
Yeah. Can I ask a question?
Please.
Yeah,
sir.
please.
Yeah. It is really next day. It is very informative, and GCMS we never use, and we had been trained, but only one single query, because I had asked to my mentor also, he had not answered. What would be the temperature to be kept for a column oven?
Sir, column oven temperature depends upon the column. Every column has got a minimum temperature and a maximum temperature. This will vary from column to column. We have columns available which can go to 350 degree or 380 degrees. We have columns which cannot go beyond 250 also. So you should know what is the maximum temperature of the column. So if the column can go to 250 or say 350, accordingly you can set the temperature of the oven. But my advice is, if the recommended maximum temperature of the column is, say, for example, 350 degrees centigrade, please don't try to cross 330. 20 degrees below that recommended temperature, column will be always in working condition for a longer period of time.
Okay. And secondly, like we have HPLC, C18 column we maximum time use to isolate isoflavonones and flavonones. What are the like other things to be isolated, can be isolated with C18 column?
C18 column is, sir, everything you are going to have a wonderful discussion day after tomorrow by my colleague from Agilent. I mean, C18 column is one of the most widely used column which can analyze variety of compounds, sir. I mean, variety of compounds. I mean, if you want personally more information, you can always contact me. I can give you more information on this.
Okay, I'll do that. I'll do that.
So this here, the time will not permit me to go deeper into that, but I can give more information. Please send me a mail or something. I can help you out, sir.
I'll do that, sir. I'll do it. Thank you for the wonderful talk. Thank you.
Sir, one more question from my side, sir. What are the reasons for peak tailing or peak fronting in GCMS, and how can we resolve that?
Yeah. So first, let us take peak fronting. Fronting is also known as leading. There are two terms, both are same, leading peak or fronting peak. So fronting means, as I told you, our aim is to get a symmetrical peak, like an isosceles triangle. I told you that. If you are dividing the peak by dropping a perpendicular from the maximum point to the baseline, this perpendicular should divide the peak into two equal halves. width of first half should be exactly equal to the width of the second half, which is called a symmetrical peak. But many times we don't get this also. So in the case of fronting peak, the width of the first half is always larger compared to the second half. The reason for fronting is you are actually overloading the column. That means your concentration of the sample is more. So what you do to reduce the fronting tendency, either you reduce the concentration of the sample that by dilution, or you reduce the sample quantity that is injected. But I will advise, rather than going for reducing the sample quantity, it is better to dilute the sample so that the concentration will get reduced and the fronting will automatically reduce. So fronting is basically because you are unnecessarily overloading the column by putting more amount of sample quantity inside it. Okay, the column has got a certain capacity. So you're exceeding that. And that's why fronting happens. So the remedy is reduce the concentration by dilution. Number one. Number two, I'm coming to tailing peak. Tailing peak is exactly opposite of this. The second half, width of the second half is always larger as compared to the width of the first half. Tailing is because many times your sample is coming out very slowly from the column, from the stationary phase. That means, in a different word, I can put the sample is getting unnecessarily, it is getting retained inside the column. There may be some active sites inside the material, inside the column. That could be one of the reasons. In the case of GC, maybe the temperature is insufficient. That could be a different reason. In the case of HPLC, maybe you are not adjusted the polarity properly. That could be one of the reasons. There are so different reasons for tailing, and we have different methods for reducing the tailing also, by adjusting the temperature, by adjusting the polarity in the case of HPLC. And in the HPLC also, we can even add small quantities of certain chemicals. These are known as mobile phase modifiers. For example, triethanolamine. Very, very small quantity of certain chemicals can be added to the mobile phase in HPLC, and that also will reduce the tailing tendency drastically. So there are different methods for reducing the tailing. So the reasons are different. Fronting reasons are different, and from tailing reasons are different, and we have effective methods, ways to control this also.
Thank you, sir. One more question. There is a can we resolve the derivatives compound, like there is some phthalate derivative compound, can be resolved by the GCMS analysis of plant extract?
Yeah, of course. Yes, of course. Once you derivative the sample, why we are actually doing the derivatization? For three reasons. One is we are converting the sample to a suitable derivative to make it more volatile, increase the volatility, number one. Number two, you are making the sample more thermally stable, number two. And number three, you are trying to increase the sensitivity. So by carrying out a suitable derivatization, you are increasing the volatility of the sample so that it can be conveniently analyzed in the GC column. You are increasing the thermal stability of the column. Again, you can conveniently analyze the sample because you are going to use a high temperature. And the third one, you are also increasing the sensitivity of analysis. So there are different derivatization methods depending upon the type of sample. Esterification is there, TMS derivatization is there, acetylation is there. Different derivatization methods are there. I got a separate whole presentation on derivatization. So we have to see what is the type of compound, and then accordingly you have to derivatize, and then it can be a plant origin sample, it can be a biological origin sample, it can be a normal chemical sample. We can derivatize, and then we can conveniently analyze it by GC or GCMS. Not a problem, sir.
Sir, but there is one question more. What is the quenching metabolomic sample, and how can we prepare? There is any method?
What is that, sir? What is the I didn't follow the question.
Quenching metabolomics.
What is that?
Quenching.
Quenching. I mean, it's not a term that is used in normally GCMS, sir.
Okay.
No, it's not normally used in GCMS.
Okay, sir. Thank you, sir. So, the participant, if you have any question, please raise your hand, then I will unmute you. Okay, there is no more questions, sir. There is a very interesting and informative session. So now I conclude today's session. Sir, can you unshare this? Thank you very much, sir.
Yeah.
Thank you, Mr. Girijan, sir, for an interesting presentation on GCMS. It's our honor and privilege to have you for this session. I especially like the session where you mentioned the importance of GCMS. You very well briefed the principal, instrumentation, and application part of the GCMS. You also beautifully differentiate the TLC, HPLC, and GCMS. Sir, with all wishes from SIRT Pharmacy, here is the token of remembrance shared on the screen. Sir, please accept this on behalf of SIRT Pharmacy.
Thank you, sir. Thank you very much. It's of very high value for me, sir.
Thank you, sir. I would like to take this opportunity to thank the person who make it possible to organize Mr. Rahul Munshi, sir. I think he is not there.
Yeah, today is not there.
From Takeswin Analytical Private Limited. Thank you, sir, for your constant support. Here I am again sharing the certificate for you.
Sir, anytime you feel any support from my sir, please contact me, sir. We are always welcome.
Yes, sir. Thank you, sir.
Ultimately, my intention was the students should benefit out of this. They should learn something new. And a lot of analytical techniques are there. We have only taken only 2 topics. And in case in future also, if you want any discussion on any other topics like thermal analysis or anything which are very, very important in pharmaceutical sector, we can have that. I am always available, sir.
Giri sir, like the way you teach us, like it is utilized by everyone. Like even the teachers, even the professors and the students, they are getting benefit out of this. Your talk. You are so
Thank you,
punctual.
sir.
Like punctuations are used nicely. Your explain quality is excellent, like fabulous.
Thank you, doctor. Thank you so much.
You are one of my great mentor I find. Like, thank you.
Thank you, sir. Thank you, doctor.
Valerie Nanni.
Okay, thank you, sir. Thank you.
Thank you, Ganesh, sir.
Thank you.
I also wish to express my gratitude to our director, sir, Dr. Jiten Manvir, sir, for providing encouragement and support. I would like to thank our patron, Engineer Sanjeev Agrawal, sir, Chairman, the SAGE Group, our Vice Chairman, sir, Dr. Prashant Jain. I would like to thank Executive Director, Ms. Sevani Agrawal, ma'am, for motivating us to do such type of events. I extended my thanks to our faculty member and student and other participant for patient listening and making this webinar series 2 an interesting one. Thank you all for making this event successful with your contribution. I would like to thank special thanks to N. Ganesh sir for joining us and sparing the time with us. Thank you, sir.
Thank you.
All. And I share a feedback link of today's session on chat box. All participants, please fill it. And there is one more information for you. For tomorrow's session, I will share a link on your mail. So with the permission of all dignitaries, I would like to end this session. Thanking for joining us. And today's session link is also available on YouTube at SIRT Pharmacy channel. So you can go through there and you can assess this today's topic anytime. Thank you, man. Thank you very much.
Thank you, sir. Thank you very much.
Bye.
And sir, you can send your email ID. I will send these presentations to you, sir, by tomorrow.
Okay, sir.
Hello, Nilesh, sir.
Yes, sir.
Yeah. No, sir. Just hope everything was as per your expectations.
Yes.
Yeah, and we again from Toshwin Analytical, we want to thank entire SAGE family for giving us a chance for present ourselves.
Thank you, Rahul Munshi, sir. You have joined with us.
Yeah. Okay, sir. In future also, we hope to conduct such type of seminars with collaboration with you, sir. Thank you very much.
Thank you.
Yeah, and thank you, Girijan, sir. Yeah.
Okay, you are welcome, Rahul.
Yes, sir. Thank you. Thank you.
This session.